So welcome back. I want to do two things in this video. The first is I want to talk about the algorithms that are used to estimate the K-means solution. The second thing that I want to do is to talk about which sorts of data sets K-means will be good at versus bad at. So a couple videos ago, I laid out the problem. The problem is we have n observations on p variables. We're going to denote that by xij. We're going to assume that each observation has come from one class. I'll call that class y sub I, where these y sub i's take a value 1 through big K. The problem is these class identifiers have not been observed. So our goal is to recover these class identifiers. K-means is designed to minimize SSE. What exactly do I mean by that? Before I started the video, I wrote out the objective function in scalar notation. So what this means is we're going to add up over all observations and all of our dimensions how far each x is from the cluster mean. So this is going to be cluster y sub I, the cluster to which observation I is assigned, variable j squared. So there are a couple things that immediately should stand out. The first is we treat differences between an x and its mean the same across all the dimensions. So each of the p dimensions contribute at the same level to this objective function. That's going to have very important implications when it comes to things like variable scaling. So if I took some dimension and I re-expressed it from centimeters into meters, well, the differences would be much smaller and I'd pay much less attention to that dimension. When I have it centimeters, I pay much more attention. If I made it millimeters, I would pay even more attention to that dimension. So something as simple as changing units will have a profound effect. Likewise, if I have x's that are highly correlated with each other, so the theater example that I talked about in the previous video would be one of those examples, what happens is those variables get counted multiple times in this objective function. So in that theater example, we had 10 different dimensions that all measured a person's attitude. If I just threw those in, attitude would get counted 10 times, whereas the other variables in that analysis, say the ease of getting there, perceived value, or whether you had early socialization towards theater, would barely get heard in this objective function. So it's better to first find those true underlying dimensions like attitude and use that so that you have a better handle of how much weight you want to give to the attitude variable. So many algorithms have been proposed to find solutions to the K-means problem. The algorithm that I describe here is basically the Hartigan-Wong algorithm from the original paper. The whole idea is if I want K clusters, I'm going to pick K starting values. So pick K observations from the list of values that we already have. These are sometimes called cluster seeds. Having selected those cluster seeds, I'm going to iterate between two steps. First, I'm going to assign every observation to the closest cluster. Now, having assigned those observations to the closest cluster, I'm going to recompute the cluster centers by just averaging the observations. I go into a lot more detail on this in an older video that I have up on YouTube, so I encourage you to watch it if this is not clear. Another feature of this algorithm that you should understand simply from looking at this algorithm is that we are assigning observations to the closest cluster centroid. The implication of this is that we're going to have a real hard time when our clusters are not round. So remember this figure that I showed you during my first cluster video from Python. What would happen if I had clusters that were shaped like crescents here? So if I had clusters that were shaped something like this, and if I pick a cluster centroid, so let's say this is a cluster centroid, and this is maybe another cluster centroid, these observations are going to be closer to this cluster centroid than to this cluster centroid. So it's going to be very hard to identify clusters that don't have nice round shapes. And we saw this back when we discussed this Python chart, where all these observations become blue, all these observations become orange. We saw it when we had these elongated clusters where there's a correlation within each cluster. And so certain observations turn green even though they're not really part of the same cluster. So K-means does a great job provided all your clusters are round and have the same diameter. Otherwise, it's going to have problems. So K-means is a very important clustering approach, and there's been a lot of work to improve the computational efficiency of the algorithm. The problem itself is NP-hard, and you should think of the algorithm that I just showed you as being a heuristic that may or may not find the optimal solution. That's why we run it multiple times, with the hope that by choosing different starting values, we can find different local minima and ultimately the global minimum. But there have been many other algorithms. So I don't have time to cover all of the algorithms that do K-means. You can go read the Wikipedia page if you're interested in some of the other ones. But I do want to discuss one of the more important methods, which is sometimes called Kmeans Plus. So the idea of Kmeans Plus is we want to spend a lot more time picking our starting seeds and pick very good seeds. So here's the algorithm that we're going to use in choosing those seeds, rather than the Hartigan-Wang approach, which was just pick K observations at random. The algorithm starts by picking the first point at random. Then what's going to happen is we're going to successively go through the data set and pick an observation that is farthest away from all existing seeds. So let me go over to my document camera and sketch this out. Let's say that I had, say, 2 x's here, and I'm going to make my life kind of easy with some well-defined clusters. So I'm going to pick an observation at random. So let's say I pick this one. The next step in this algorithm is to evaluate the distance between every other observation in this data set and that observation, and choose the one that is greatest. So I'm just eyeballing this here. I think this observation, maybe right here, is the one that is furthest away from this one. Well, the next step that we're going to follow is compute the distance between every observation and this point. We've already computed the distances with this point. And we're going to take the observation that is furthest away from both of these. We're going to take the minimum of the distances between these two and then select the maximum value, which I think is going to be this one. Why? Because that distance and this distance will be as large as possible. So the minimum of these distances is going to be this guy, and that's going to be as large as possible. And so in this simple example, clearly I picked 3 pretty good seeds because they're all in different clusters. Whereas if I just picked observations at random, there'd be a good chance that I'd get, say, 2 seeds from this cluster, and it would take more iteration for that center to drift over and get to the right cluster. Having chosen these seeds, instead of iterating between the two, we're going to take a single pass. So for each remaining observation, what we're going to do is assign it to the closest centroid. So in this case, let's say this is the next observation. I would have to evaluate the distances between my 3 centroids, and it would get assigned to this one. Then what I do is I recompute the centroid. So I adjust the centroid, and the new centroid is going to be right in the middle. Then I would take the next observation. And so maybe my next observation in the data set is over here. I would compute the distances between my 3 centroids, this, and this. Clearly this one's going to go over here. And then I would recompute my centroid. With that added in, my centroid drifts over here. Maybe this is the next observation. And I would do that for each observation, and the algorithm would terminate. So rather than taking multiple passes of order n, this is going to do things in a single pass, and you can see where it would be substantially faster. If we look back at the Python page, you can see they actually recommend something called mini-batch k-means. You can read about that on Wikipedia. The basic idea here is to reduce computations by using random subsets for each iteration. You may lose a little bit of performance in terms of SSE, but in practice, people have found that reduction to be quite small. Let me now make a few comments about k-means. K-means is one of the most popular clustering algorithms. You're going to find it in all the major statistics and machine learning packages, and it's without a doubt one of the most popular methods, even though it has quite a few limitations. So as I mentioned earlier, the optimization problem that k-means is solving is NP-hard, but we have a lot of good heuristics that enable us to define clusters on very large data sets. So I routinely will run this on hundreds of thousands of cases without any problems, and that's just on a laptop. To avoid the problem of local minima, as I mentioned earlier, you should be running with multiple initial seeds, and then the way to get reproducibility is to set the random seed before you run it. Software implementations usually let you cap the number of iterations so the thing doesn't get into some infinite loop. I usually set this to be quite large. I also set the convergence criteria. So the convergence criteria being, if we were iterating with Hartigan-Wang, what's the change in the objective function between two iterations? That's one of the common convergence criteria. I tend to set that quite small. The default maximum number of iterations in R is quite small. The reasoning there is that you see very little improvement in the objective function after a handful of observations, but it does improve somewhat. So this is a judgment call that you'll have to make. So k-means has a number of limitations that you should understand. So k-means is sensitive to variable scaling. The partial fix is transform your data ahead of time. Problem number 2 is because k-means uses these Euclidean distances, we're implicitly assuming spherical clusters, which have equal variance in all directions, as well as across clusters. There are a number of famous illustrations of this bias. So we've already seen one in the Python figure, where here we have 3 different clusters with different variances. They're all round, but they have different amounts of variance. We see where k-means wants the smaller variance clusters to swallow up cases from the larger ones. So those orange cases out here probably should be green. Another very famous example is called the mouse dataset. So the mouse dataset consists of one large cluster, 2 small clusters that look a little bit like the face and ears of a mouse. When we run k-means, we see exactly the same thing where the clusters that have smaller variances tend to swallow up a lot of the observations for the cluster with a large variance. We are going to get into Gaussian mixtures next, and you're going to see Gaussian mixtures excels for this particular problem. Another well-known limitation is that there's a bias towards producing equal-sized clusters. To see why this is the case, let's go over to my document camera, and I'm going to sketch out an example for us. So let's say that we have x1 and x2, and I'll make it easy for k-means by having the same variance. So let's not have that as a problem. So I've got one cluster out here with a lot of points. So nice round cluster there. And then let's say I have another cluster out here that's fairly sparse, but it is distinct. It is another cluster. So I've got a lot more observations here. This is very dense. Let me just really fill that in. And this one only has a few cases. So maybe only 10% of my cases come here, 90% come here. Well, if you're the k-means algorithm and you're trying to minimize the sum of within cluster variation, the real centroid is here, but if you were to move the cluster centroid a little bit in this direction, what would happen? Well, your SSE would get a little bit worse on a few points, but for these points that are kind of close to no man's land, you would you might be able to do a bit better, and then all these observations down here, the cluster centroid is going to drift in this direction. You do substantially better down here. So as a consequence, if I have very few observations here, K-means can sacrifice some of the accuracy on this cluster by swallowing up cases on the very dense cluster, and that's why K-means is going to have a bias towards producing more equal sized clusters than, say, 90-10. Finally, because of the hard assignment, by hard assignment I mean K-means assumes that every observation is assigned to one cluster only. K-means is going to give biased estimates of the means and variances. To understand why this is the case, I'm going to propose a little example for us. So let's say this is 0. And let's say that I have observed p equal to 1 dimensions. Suppose that I have some number mu, and this is negative mu, that is the cluster centroid of my two clusters. So here is one of my clusters. Here is the other cluster. I'm going to assume that both of these have the same variance, sigma. So this ought to be the perfect case for K-means, where my variances are the same. I've got quite a bit of distance between these two cluster means. Now, I'm going to make life even easier for K-means and give it mu and minus mu as the starting values. So this is the absolute perfect world for K-means. What's the next thing that K-means is going to do? It will assign every observation to the closest cluster centroid. With these as starting values, all observations less than 0 are going to get assigned to negative mu, this mean. All observations greater than 0 get assigned here. All right, fine. And so what that means is all the observations in this tail of the right distribution are going to will be assigned to the wrong cluster, and all observations in the right tail of the left cluster get assigned to the wrong cluster. Well, what does K-means do next? Well, the next thing that it's going to do is recompute the cluster centroids. This is where we end up with a big problem, because when I compute the average of all the cases that have been assigned to this cluster, what's happened is we're missing this tail. So with this tail and this other tail that I have, the center is right here. If I get rid of this tail, and I actually add a bunch of cases over here, what's going to happen is the left tail is going to cause the mean to drift outward. Likewise over here, the mean is going to drift out when I compute the average of all those cases. So what we would expect is that the means will be overestimated because of the overlapping tails being truncated. What about the variances? Well, both of these distributions have a standard deviation of sigma when you have two tails. As soon as you get rid of one of those tails, there is going to be a downward bias in the standard deviation. So because I have omitted this tail, it's going to appear that the standard deviation is lower than what it should be. Now, as the clusters become better separated, so for example, if I had a situation like this, where there's almost no overlap, then those biases go away. But in a practical situation where you have a lot of overlap, these biases can be quite pronounced. You're going to have a homework problem where I ask you to investigate those biases. What we're going to see is that Gaussian mixtures will address most of these issues, but it's not going to be practical to use on large data sets. There are also a lot more modeling decisions that are going to have to be made. So do you want a simple method that you can run on very big data sets, or do you want a fancier method with more parameters to adjust and a lot more complexity in finding the solution, but is capable of avoiding these biases? So I mentioned that K-means is sensitive to starting values. Let's go back to my newspaper example for a minute, and I'm going to run 100 different solutions. So I set my seed once, and I run this 100 times. I'm going to store the estimated solution. We're going to set max iter equal to 100. We're going to store the best solution from each of those 100 runs, and then I'll plot them. So here are the estimated cluster centroids, and you're going to see they're kind of all over the place. The ones that have a red triangle above them are the optimal solutions. So you get your non-readers, your light readers, your heavy readers, your skimmers, and your selectives. But there's a lot of different solutions that I could be coming up with. If you look at the mean squared error values, here's a histogram. And it looks like with the majority of my starting values, I get the optimal solution or something pretty close to it. The problem is almost half the time, I get solutions that are pretty bad. In some cases, horrible. So getting a solution that's over 2 when the correct value is 1.4 is a pretty poor local minimum. This is something you should be worried about when you use K-means, and the solution to this is to run the algorithm on enough initial starting values so that hopefully you're avoiding these really poor solutions. I'd now like to create some synthetic data sets that illustrate how K-means can be broken. So let's start out with the perfect case for K-means. So if you look at my R code here, you can duplicate all of this because I've set my seed ahead of time. You're going to see that I've generated 2 clusters, one with a center at 0, 0, the other with the center at 3, 0. Both of these clusters have a within cluster standard deviation of 1. So I'm just taking z values in both the x1 and the x2 direction. So we have 2 round clusters. This is the perfect situation. If I run K-means, here's the answer. Any value that is circled gets misclassified. And so let's just compare these for a second. You're going to see this red triangle up here is quite far from the center. It's actually closer to the black center. And therefore, when we assign it to the closest cluster centroid, it's slightly closer to the black center, so it gets assigned there, but technically it's misclassified. You're not going to be able to do much about those overlapping cases. When we get to Gaussian mixtures, we're going to be able to assign a probability and say that all these observations along the border are really hard to classify, and there's a lot of uncertainty with them. They could just as easily come from the red or the black, whereas these observations off to the right or left have very little uncertainty with them. These are definitely black and these are definitely red. Now, what I said earlier is that K-means is sensitive to multicollinearity. So I'm going to simulate multicollinearity by simply making some copies of x2. So I've created 3 copies of x2. Now notice what's going to happen when I run the algorithm. x2 is going to get counted 4 times in the objective function, whereas x1 only gets counted once. As a consequence, vertical deviations get penalized 4 times as much, and the clusters we end up with look more, there's one that's mostly above 0 and another one that's mostly below 0, rather than splitting it vertically the way it should be splitted. We could get the exact same solution if we change the units of x2. So in this example, I'm going to multiply every value of x2 by 2. This would be like changing units, going from centimeters to inches. Instead of dividing the clusters here at roughly 1.5 vertically, we have something that's more of a horizontal cut, dividing the 2 cluster centroids. So what happens if we have different numbers of observations? What you're going to see is my right cluster now only has 50 cases. So the red one only has 50 cases. The black cluster has 100 cases. When I run the cluster solution, what you're going to see is just what I predicted earlier. The red centroid is going to drift to the left so that it can swallow up a lot of these black cases. That's going to allow the black centroid to drift a little bit to the left. So you'll see those biases down here in the estimated means, which would reduce the overall error of the cluster solution. So x1, rather than having a mean of 3 in the red group, is only 2.7. Rather than having a mean of 0 for the black cluster is going to be minus 0.08. In this example, let's have the same number of observations in each cluster, but I'm going to make the variance of the right cluster much smaller than the black one. So this is a little bit like the mouse example. And just as with the mouse example, we see the red cluster is swallowing up observations that should be black. Finally, what happens if we don't have round clusters? So the way I've generated observations here is the black cluster is still going to be round, but the red cluster is going to have a within cluster correlation. So if you look at the red observations, there is a positive association. It's actually a correlation of 0.8 between x1 and x2. Now when we run k-means, what we see is a mess. So all of these observations that are really in the left tails are getting assigned to the black cluster, and the estimate, and only about a third of the cases get assigned to the red cluster at all. So K-means has a really hard time with this. Well, as a sneak preview of where we're going to go, here's the solution that you get using a Gaussian mixture. You can see that the Gaussian mixture has clearly found the round cluster as well as the ellipsoidal cluster, and also found that roughly half the cases are in both clusters.